Good evening. How are you today?
Hi, I'm good. How are you?
I'm doing well. Just getting set up here.
Good. As you probably see by my name, I'm the intern interpreter, so I probably won't be actually interpreting for a little bit because I'm training to become one. But thank you so much for helping me learn from seeing the other interpreters do what they do.
No problem at all. If there's anything I can do to help, just let me know.
Okay, perfect. Thank you.
Good evening, Ananda.
Good evening.
We'll be getting started in about 10 minutes or so. Thanks for your patience. We'll be getting started in about 10 minutes or so. Thanks for your patience. Someone has an open mic. If you could mute yourself, please. Thanks. All right, it's 5:30, so I'm gonna go ahead and begin today's class. Uh, just to remind you, I am recording our meetings, and I will be sharing the videos in the announcements. I put the 2 videos from last week in the announcements. If you need to review it, feel free. It's there for your use. Somebody's got an open mic. Please mute yourself. All right, so I'm going to go ahead and share my screen. What you should be seeing now is the course homepage. Is everybody seeing this? Somebody just let me know, yes or no.
Yes.
Yes.
Thank you. Thank you. I always like to verify. Okay, so before we jump into this week's material, I want to, um, I guess, take some time to see if there are any questions about anything that you might have come across in reviewing the layout and structure and materials for the course. Just feel free and unmute your mic and ask your question. Okay, well, I'll take that silence to mean that everybody is okay with finding what they need for the course. And so I want to remind you, you should be seeing the last page of the syllabus on the screen now. If you have not sent a signed copy of the last page of the syllabus for this course, you need to get it to me. So you have options. You can print the form, sign it, date it, and scan it, or take a picture and email it to me.
And that's on what page?
That's the last page of the syllabus.
Okay.
So
And that's for both classes, right?
that's for both classes. Each class has its own syllabus. So one of the things you would have, should have noticed in working through week 1 was that I asked you to send this page to me. So if you've not done so, you still have that left on your plate to do. So, get it to me hopefully today after we're done. But if not today, then definitely here in the next day or so. By Wednesday's class, I should have signed syllabi from everybody. So make sure you get that done. All right. So let me go into the weekly overviews. I remind you that the weekly overviews is where you find the breakdown for each week of the course in terms of the topics that we cover, the due dates, and the learning material. So if you notice this week, we have two topics that we have to tackle. One of them is the nature of science, and the other is measurement. So what I'm going to do is I'm going to go into the nature of science overview, and listed here are the objectives for the week. So you can see we're going to be looking at the scientific method. We'll look at the relationship between science and technology. We'll get to solving some simple problems using derived quantities and derived properties. We'll look at the idea of, estimating. You'll be exposed to the SI base units and prefixes. And then, of course, for every week, one of the things you have to accomplish is to be able to discuss the material that we've covered with your classmates, okay? So here are the activities that you have on your plate for the week. I'm gonna talk about the project on Wednesday. I'll give an introduction to the project then. So we'll just kind of put that on the back burner for right now. Hopefully you've taken a look. I did post an announcement telling you to go ahead and get started, but we'll take a look at what you need to be doing for the project, and we'll do that on Wednesday. And then here are some learning materials, resources to help you in dealing with this nature of science topic, okay? So I've given you some notes and some videos that can help you. And then I'm going to be covering these notes that have supplemental in front of them. Those are my lecture notes that I make available to you. Okay. So I'm going to go ahead and open that up. All right. So let me see if I can move that over here. Yeah. All right. So now in every one of my note packets, there's this information on how to study. A lot of times, especially in a science class, students are wondering, what's the best approach? What do I need to do to be successful in this course? And so one of the things I like to do is stress, how you should be preparing in terms of dealing with the material, okay? So, of course, it goes without saying that by now you should have taken a look at the syllabus. Whenever you approach a new unit of material or a new topic, it's important to know, any key terms. For example, today we'll be looking at the idea of a property or quantity. And, if you're not familiar with what we mean, then that kind of puts you at a disadvantage. So you want to make sure that you understand any relevant terms. I'm providing my notes, but that doesn't bar you from taking your own notes. I would encourage that. I would also encourage that you review. Somebody's got an open mic, please mute yourself. Okay. So again, you want to be diligent and actually look at the resources and required readings and viewings that I've made available to you, because if you're not doing that, then you're limiting your opportunity to really grasp fully the content. Of course, you need to do all of the assignments that are being, that are put out for you to complete, because again, this is an opportunity to engage with the material. And it's also an opportunity to see where you might be having questions, and then you want to ask those questions as soon as possible. Sharing and discussing with your classmates is vital. And that's why for every topic you do a discussion. And then, you know, uh, I've always kind of stressed to students that if you're not reviewing the notes in the materials that are available to you on a regular basis, then um, it makes it very difficult for you to process this material from a long-term perspective, right? Not just immediately, your immediate interaction, but you want to, as I always say, take this material from short-term memory to long-term memory so that it sticks with you, all right? And then of course, you know, you'll have opportunity for assessments like midterm, final, so on and so forth. So there's an organized way that you approach this material. And so I like to outline that for students so that, you know, you get the most out of this stuff, okay? And so in this particular packet, we're gonna be focusing on the connection, the scientific method. You know, what are the steps of the scientific method? How do you use it? We'll look at an example. And then underneath all that, we'll be looking at as well the connection between science and technology, so that you know you form a basis for understanding how we arrive at the knowledge and information that we currently have in physical science. Okay, so you know, it goes without saying that there are many different ways that we can process our environment. Okay. But science offers us a way, not the only way, but a way to help us understand our surroundings, understanding nature, understanding the rules and patterns that help us to explain the phenomena that we see happening in nature. And so, you know, we operate in science with the idea that nature has an order and a simplicity. And if we investigate, we're able to understand and describe and reveal this underlying order. Okay. But science, again, is just a way. Okay. And we package the knowledge that we have about nature and how it operates in the form of theories and laws. And so these theories and laws are used to express our understanding of nature. Okay. Now, we have to be mindful of the fact that these laws and theories do help us understand nature, but they are not set in stone. They represent our best understanding of nature, which can change as we develop better kinds of technology. And we'll look at that here shortly. So because nature, those you know, orderly and you know, simple or simplistic, if you will, there's a wide range of phenomena that happen in nature. And so, you know, we have different categories of science because different areas or content areas or disciplines focus on different aspects of nature. So you see some listed here: astronomy, chemistry, biology, geology, and physics. Now, in this class, I'm always upfront with students. Your primary focus is physics. This is an introductory physics course, but we go light on the math, if you will. Most physics classes are, you know, they're math intensive, but here We focus heavily on the concepts and we use simple math to try to help us understand those concepts. We will get to some astronomy in this course as well, but chemistry, biology, geology, those are not topic areas that we focus on in this particular class. Okay, so just to make sure that we know what area we're focusing on. And I would tell students that you know physics, though complicated in most folks' minds, is a very beautiful science. Okay, and that's because physics really does get down to the most fundamental level of how nature behaves. And so we deal with a lot of different things: energy, matter, space, and time, and how each of those um, properties interact with each other. Okay. And so I always tell folk, physicists want to know everything about everything because we want to be able to understand every phenomena that can be measured and tested. And that's quite a bit. But physics at its core is a very fundamental science, a very basic science. Okay. And so, so here it says, you know, since we're interested in uncovering and understanding the fundamental aspects of the universe, the other scientific disciplines like biology and chemistry um, have to, you know, we come up with some rules and patterns and laws and theories, and those other branches of science have to incorporate that. In other words, however, whatever they're attempting to explain must match or gel with physics and the laws that physicists have, uncovered. Okay, so I tell students, you're here to learn a lot, but at a very basic and introductory level. You're also, we're also going to be looking at not just what are those laws and theories, but how we apply them. Okay. You can think of this physics as broken down into two categories. Um, Theoretical kind of physics, where we just want knowledge for knowledge's sake, and then applied physics, where we take the knowledge that we have and we find ways to use it. And we typically think of this idea of applications of physics as very closely matched to the idea of technology. So when we find new and greater technologies that can help us to get a better understanding of our physical environment. So you can think of it this way. It's kind of like a cyclical process. We get more knowledge, we get better technology, we get better technology, we get more knowledge. So that's what they're referring to here. When engineers develop new devices and systems, they have to rely on the theoretical or the physical laws that are relevant. And so you can see here, engineering, electrical and mechanical, all rely on applied physics. Some folk like to sometimes say that, engineering is applied physics, but there's other aspects of engineering beyond applied physics. But at its core, when engineers want to come up and develop better technology, they do rely heavily on physics. Um, Even disciplines like architecture, they have to rely on the laws of physics because they have to worry about things like whether what they're designing is it structurally sound. They have to worry about things like heating, cooling, lighting. All of those rely heavily on physics. So, the goal here, because I doubt, I'm not 100% sure, but I'm pretty confident that most of you aren't trying to be physicists, but, even in your daily life, you need to have some understanding of how things function and, how nature behaves. And so that's at its core what you're here to get an understanding of. I always tell students it's really important up front that you know what animal you're dealing with. Okay. And so your animal in this class is physics, introductory level physics. So how did we come up with this body of knowledge and the body, and the applications of that body of knowledge, um, that we call physics? I always tell students, how did that stuff get in the physics book anyway, right? Um, and so there has to be some um, methodology or process that scientists engage in. Okay, and so um, at the cornerstone, or at the most basic level, um, our understanding of our physical environment starts with the observation. Okay, and so then from observations, scientists can then start to formulate rules or laws or understand patterns in nature, in whatever phenomena they're observing. Okay, and so they said here, for example, some observations can be done directly. Okay, and then there are other phenomena such as, the motion of atoms and molecules that can't be seen directly, but through indirect measurement and observations, we can understand those phenomena. But you have, at the start of the whole scientific process is the idea of an observation. And then after that becomes the attempt to explain that observation. And so it's important that you understand the different ways we package the knowledge that we get from those observations, from our investigations, from our experimentation. Um, and so one of the key things that helps us to understand is by making models, scientific models. This is a simplified representation of a system or phenomena. So we've observed the phenomena. We want to model that phenomena in a way that helps us gain a better understanding. Okay. So, we, as I mentioned, for example, we can't directly observe atoms and molecules that make up a gas, for example. Um, but the but in order to help us understand these atoms, we can model them. And so you're one of the most simplistic models of an atom is to um, set it up like a planet that orbits the sun. Okay, so we can model the atom as having a nucleus that's like the sun and these electrons that move around in orbits much like the planets do. And that's a highly simplified representation, but it's a start in helping us understand how atoms behave, for example. Okay, So now, once we have observed the phenomena and we've um, gathered evidence through reproducible experiments, many times we package that knowledge as a theory. So I want you to understand that most times when folks say a theory about something, they take it to mean that we're guessing, we really don't know. That science is totally, put it this way, science doesn't operate that way. What we package in a theory is those things that we have been able to observe and verify through experiment. So we've, I always tell students a theory is kind of a broad explanation for a phenomena that we see in nature, that we have synthesized through great many observations, multiple experiments done by many different types of scientists, pure and applied. And so the outcome of those observations and experimentation is packaged as a theory. So what's in the theory package is the evidence that we have collected regarding a particular phenomena. And it's very broad, okay? But what's not part of a theory is just, we're just guessing and we're not really sure. That's not that's not the way we operate in science. Where, I tell students, no, we're not just guessing. This is what we have been able to observe and verify. All the evidence that we've collected regarding a particular phenomena points in this direction. Okay. A law, on the other hand, is not quite as broad as a theory. A law focuses on a particular pattern in nature. Okay. It's more singular. All right. And so you see, in theory, it's patterns. In a law, it's a pattern. Okay. And so, yes, it is supported through evidence, scientific evidence by experiments, but the scientific law is explaining a singular phenomena. Okay. And that's why many times a law can often be expressed in a single mathematical equation. And they give the example of F equals ma. So a theory is a very broad explanation of a phenomena based on multiple patterns. A scientific law is more singular and more narrow in its focus, and focuses on a specific phenomena that can be described using a single mathematical equation. All right. So you see, that's why it says here, a law describes a single action, whereas a theory explains a group of related phenomena. Okay. So that's important. That's important because if you're going to be looking into physical science, some of the knowledge that we have is packaged as theories. For example, the Big Bang theory or the theory of relativity. And some of the knowledge that you're going to be encountering is packaged as a law, like Newton's second law. Okay. And so, what you need to be comfortable with is, how do we operate in this environment? How did we get to this knowledge that we call physical science? How do we go about the process of physical science? So how do we go about investigating phenomena and uncovering new knowledge and ways to use that knowledge. Well, in physical science, we use the scientific method. Now, other branches of science use that as well. But we're trying to be what more focused from the perspective of the branches of science. We're trying to be more focused on the how we do things in physics, if you will. All right. So um, to be able to come up with an accurate description of a phenomena, scientists rely on this systematic and orderly process known as the scientific method. I tell students the scientific method is a problem solving process. That's what it is at its core. Okay. And it's a problem solving process that's more uh, uh, fitting to the kinds of investigations we do in science. Okay. So because you can solve problems in all disciplines, in all aspects of life, right? You could be trying to start up a business and go through a problem solving process. But we're looking at the problem solving process that's customized or tailor made for scientific investigations. All right. And so, as I said, this whole um, scientific endeavor, this scientific method process starts with an observation or, and a question, something that the scientist wants to investigate or research. Okay. And so once the scientist has formulated the question or the problem that's going to be tackled, they then have to go out and perform research on that topic. So, a lot of times folk think that you do the research before you formulate the question, but in many in many investigations, a lot of the research happens once you have come up with a problem or a question that's going to be investigated. And so I tell students you have to be careful there, right? Because you don't want to spend time solving a problem that's already been solved, right? So it's important once you formulate a question to say, what's already been investigated in this area? And so scientists will have to do an exhaustive, uh, you know, investigation of the research and experiments that have already been done in that area. And then typically what happens is once a gap in the knowledge has been identified, then the scientist can construct a hypothesis to guide that investigation. Okay. So what is the question that we're going to be looking into? Let's see what's already been done in that area. Now formulate a hypothesis that will guide the investigation that we're about to do. And what is this hypothesis? Well, it's important to be clear on that. A hypothesis is a testable prediction based on the research that was done. A testable prediction. See, this is where we start to differ from other problem solving processes that might be used in other areas, because in science it has to be testable. Okay. Some other problem solving processes or some other type of phenomena that are going to be investigated might not require that what you're guessing at be testable, but in science it has to be. Sometimes you hear the hypothesis referred to as an educated guess, and I tell folk, please don't leave out that educated part, because that is critical. Otherwise it's an opinion. Okay. If it is not based in our current knowledge, then, you know, and it's not testable, then it's not science. Nothing wrong with those things. I tell folk all the time, it's great to have an opinion about things. But in science, we're more interested in looking into those phenomena in a way that we can test. Okay. And so if the hypothesis is a testable prediction, then what comes next is that the scientist performs an experiment to test whether or not the hypothesis is correct. So in that experiment, and those of you in lab class, you'll be doing experiments. So that experiment has to be done in an orderly fashion. It has to be reproducible. There's, you know, data collected, an analysis and conclusions drawn during that experiment. And in that out of that experimental process, the scientist is able to confirm whether the hypothesis was correct or not. Sometimes, if the hypothesis is not correct, the scientist has to figure out, how do I need to modify my experiment to continue this investigation? You know, if I can tweak my experiment, then I can move forward in trying to you know, continue the investigation. Or the scientists might decide, you know, the hypothesis was so far off that we need to formulate a new hypothesis. In the event that the hypothesis is confirmed, that's not the end. Because even if the scientist confirms the hypothesis, somebody else has to be able to reproduce that experiment and also confirm the hypothesis. I tell folk, we aren't going to rewrite the textbook because somebody did an experiment and that single experiment is contrary to all 1,000 other experiments that have been done in that area, right? So reproducibility, validity are all important when a scientist is conducting an experiment, because that often guides the future work that will be done. All right, so the scientific method is a problem-solving process that is tailor-made for the kinds of things, the kinds of investigations we do in science. And so here's the basic sequence followed in the scientific method. So again, question, research, hypothesis, experiment, data, conclusions. Now, in some textbooks, you'll see them broken down a little bit differently. They may even list the observation as step number 1, and they may incorporate data and conclusions into the experiment. And then maybe sometimes they'll have another step that says experiment, data, results, conclusion. To me, that's not the major issue, whether they have, you know, combined steps or they've added a step. It's the overall way that the problem is tackled, right? So whether they have 6 steps or 7 steps or 5, as long as within those steps, they're following an orderly way of doing things that can be verified and reproduced, then that's what we're after, okay? So if you open another textbook and you see it broken down a little bit differently, that don't think that this is wrong or that's wrong. Think of it as, you know, it was really of consequences. What are they actually doing in those steps? Okay. So you'll have an opportunity on problem set number 1 to actually utilize the scientific method. But I wanted to show you an example, okay? Now, I'll be honest with you right up front. This example is a little bit over the top, really, but what I'm trying to do here is to get you thinking about, you know, how we actually utilize the scientific method, okay? So here's an example. There's someone having a burning, you burning passion and wanting to know, when the Titanic sank, what happened to the water level on shore? Now, probably nobody's really like, dying to investigate this question, but I just thought it was like a way to illustrate the scientific method. Okay. So, before the person can formulate a hypothesis, they've got to go out and read and synthesize all information available on the sinking of the Titanic. How big was the Titanic? What material was it made of? How cold was the water? How many icebergs? What are the size of these icebergs? All information relating to the sinking of the Titanic has to be, synthesized before the hypothesis is formed. And so based on all of that information, the scientist has to say, okay, based on everything I've read, this is my hypothesis. The water level rose, the water level dropped, the water level stayed the same. One of those, right? It could be any of those three, depending upon the information that the scientists found when they did their research. Okay. So now the next thing is you've got to test this hypothesis, right? Now, truthfully, you aren't going to be able to go back and resink the Titanic. Okay. So the question then becomes, well, how do you actually test this in an experiment? Well, you see, that is impacted by the resources that you have available. Because I tell folk, if you got unlimited resources, unlimited money and time and all of those things, maybe you can have somebody build you, a to the letter replica of the Titanic. And, and maybe, I don't think you'll get any people involved in this test though, honestly, because we know how it ends, right? So maybe they're going to be, utilize, the crash test dummies or whatever they're going to use, right? As people in this whole thing. And, maybe they've got somebody at a monitoring station watching the North Atlantic to make sure the temperature's just right, the amount of fog and the icebergs that are available are, so what's important here is that the resources that you have available are going to impact the kind of experiment that you do. And the kind of experiment that you do and the quality of the experiment is going to impact the data and the results and the conclusions that you're able to draw, right? Because if you do a flawed experiment, then you don't expect to get results that can be relied upon, right? And also when you're doing this experiment, this is kind of where ethics and things come into play, right? Because whether your experiment is fundamentally sound and your results come out not so good, you still have to be open and ethical about how you report that information, right? because ultimately, you have the potential of impacting people's lives, and um, that's pretty critical. I mean, I'm sure all of you have seen or heard these commercials where they say, if you have taken this medication and died, or if you've had some terrible results, terrible health consequences as a result, call this lawyer's office. And the question you have to ask yourself is, didn't those manufacturers or pharmaceutical companies know that this product was going to give, 20% of the people who took it heart issues, or, some type of adverse results? And so, you wonder, were they being ethical when they reported their findings and got approval, right? In fact, we just saw this happen few months back with one of the vaccines for COVID, right? The manufacturer put it out there, and then not long after had to actually stop administering it, because some of the folk who took the vaccine were having some major health issues, right? And so, you wonder, well, yeah, was that because they kind of overlooked some things that were actually happening in the trials? So you see, this experiment part of uncovering knowledge is critical, and that's where resources, ethics, all of those important things come into this whole problem solving process. Okay. Um, And so after you've done the experiment, of course, you analyze the data to see what happened during the experiment. Um, and then you can draw conclusions. Was your hypothesis correct? Do you need to test further? Okay. So just be mindful of the fact that, our goal in science is to help explain how our environment works. And in particular, in physical science, I always tell students we're doing scratch and sniff science, because we want to know how our physical environment works. And we do that through observation, experimentation, and we package that knowledge in the form of theories, laws, postulates, so on and so forth. Okay. So this is just like a kind of a look at the historical roots of physics. um, Physics started out as more of along the lines of philosophy. Okay. And that's because it had, we typically think of it starting with the Greeks, because we give credit to the Greeks for being the culture that um, start to think that things could be investigated and explained through um, through experimentation, as opposed to what we like to think of as kind of along the lines of mythology, if you will, right? The Greeks were starting to think that there are natural there are there are natural explanations for these phenomena. Okay. And so they're using their intellect to help explain how nature works. Okay. Um, So while they did experiment, like I said, they were starting that, we give credit to them for starting that process, but still they thought that they could reason through most phenomena. Okay. And then you get to what we call classical physics. And Galileo is one of the important figures, because he really started to move beyond these philosophical explanations, um, for explanations based on repeated testing. Okay. And so, this whole idea of physics in terms of study and motion, he was key to helping us begin that understanding. And we will be spending a great deal of time in this class looking at moving objects. And so Galileo's um, giving credit for, Galileo is giving credit for starting that whole process of understanding motion. And then we move beyond Galileo to Isaac Newton. In fact, what you are studying in this class, we typically refer to as Newtonian physics, because it's the explanation of motion and gravity, um, utilizing the laws that Isaac Newton came up with. And so his discoveries form the bedrock of what we call classical physics. And so that's where we're going in this class. An understanding of our physical environment based on the work of Isaac Newton and some of his contemporaries. Okay. Modern physics. We don't get too much into modern physics in here, because then to get into modern physics, you move past the laws that Newton and folk like Kepler came up with for more recent theories like relativity and quantum mechanics based on the work of Albert Einstein and Niels Bohr and other modern physicists. So relativity, quantum mechanics, while some of you may choose these areas as far as the project goes, as far as the content that we'll be relying on in this course in terms of, each week what we'll be covering, those mostly tie into classical physics and Newtonian physics, okay? So just to kind of recap in this package, the nature of science, one of the most important things is the scientific method, because through the scientific method, you have an orderly way of problem solving, and you'll have an opportunity to utilize, to do your own kind of over the top utilization or application of the scientific method in the problem set that you're going to be tackling. Okay. So in this particular packet, we're going to be looking at an introduction to measurement. And what I want to do is basically introduce you to the metric system. Okay. So before we can jump specifically into that, we have to understand, what are we using this stuff for? What are we using this metric system for? Well, in physical science, we observe and then we quantify. Okay. So I tell students, everything that is in the physical science textbook is based on observation and measurement. Because as I stated, there are many different ways of explaining our physical environment. Roses are red, violets are blue. I just described something in my physical environment. But the issue with that is that it's ambiguous, because if I say a rose is red, am I talking ruby red, blood red, orange red? What? Or violets are blue? Are they midnight blue, baby blue, sky blue? See, there's too much touchy-feely language there for it to be specific. When I use language like that, it's open to interpretation. Also, everybody might not know what red means. So if I say roses are red and you're like, what's red? What does that mean? What's a rose? Okay. But when we move beyond that kind of language that's open to interpretation and to a more quantitative description, then that is um, it can't, it's not open to interpretation. Okay, and so that's where we want to go. So I like, if we were in a physical classroom, and you can think of our space now as a physical classroom, some of you might be feeling like, oh, our physical classroom is too hot or too cold, or it's just right. And then, but if I look at the thermostat, for example, and I say it's 72 degrees Fahrenheit in our physical classroom, there's not much debating on that. Okay. So the reason we go to this quantitative description is because we want to make sure that the understanding for everybody is the same. Okay. And so in order to quantify, we need to understand, well, what is a physical quantity? It's something that can be measured. It's a property of our environment or an object that can be measured or calculated from other measurements. To me, that's still measuring, because it, at its core, it is all relying on measurement. Okay. And so what we're going to be relying on are some fundamental properties or quantities to help us in physical science. There are some fundamental properties or quantities that are measured that we utilize in physical science, and we're going to be working with those. Okay. And so they give some examples here: distance and time, right? You can measure distance, you can measure time. And then, you could utilize those measurements to calculate another property like average speed. All right. So what we've got to get at now is, how does this measurement business work? So anytime we measure a physical quantity, there's a number part of that measurement, and there's a unit part of that measurement. So we're going to be taking a look at these units that are relevant for physical science. So see how very quickly we move from, this is the process that we use when we want to gather information, and a key part of that whole process is measurement. Okay. And so when we measure, as I mentioned, there's a number and a unit. For every physical property that we measure, there's a number and a unit. The number part, that's easy enough to understand. You know your numbers. I don't have to teach you your numbers. But what we do have to get on board with is this idea of units. Okay. And that's because we want to all be using the same units, right? Because conceivably, every person could make up their own units. I'm using paper clips and you're using diddly wings. And the question then becomes, well, how do I know how my paper clips compare to your diddly wings? Well, we solve that issue by having unit systems. Okay. And so physical science relies on the SI system. SI stands for System International, also known as the metric system. There's also use of English units, the English system of units, and we use that in the United States widely, right? Things like inches, feet, miles, gallons. Those are all part of the English unit system. And while, in your everyday life, you probably use them quite a bit, even if you don't realize it, But in physical science, and in particular in this class, we're going to focus heavily on the SI or metric system of units. Now, in the metric system, we utilize 4 fundamental properties. 4 fundamental properties, okay? When I say fundamental, I mean at the core of our physical environment are these 4 fundamental properties: length, mass, time, and temperature. Not electric current, because we don't do electric current in this course. So length, mass, time, and temperature. Those are our 4 fundamental properties, 4 fundamental quantities of nature. What am I saying? At this level of a course, everything we're going to learn deals with those 4 fundamental properties: length, mass, time, and temperature. Now, you might be thinking, well, 4 things. How difficult could this course be, right? 4 things, we can finish this tonight and move on to the next thing. But here's the thing. You can make an awful lot of combinations with those 4 fundamental properties. And that's where we have to, that's where sometimes the difficulty comes in, right? The other thing is that there are base units associated with those fundamental properties. And in the metric system, the fundamental unit for length is the meter. The fundamental unit for mass is the kilogram, not the gram. The gram is for chemistry. The kilogram is the fundamental unit of mass in the metric system. The fundamental unit for time is the second, and the fundamental unit for temperature is Kelvin. Okay? So everything we're going to be studying in physical science is based on measurement. And we're going to be using the metric system to help us understand those measurements that constitute physical science. And in the metric system, there are 4 fundamental properties: length, mass, time, and temperature. And the fundamental units that go along with those properties in the metric system are meter, kilogram, second, Kelvin. Now, there are other unit systems, and they have their fundamental units and fundamental properties, but we're going to stick to those, okay? And so you see here, ignore that last column or replace it with temperature and put Kelvin, and the abbreviation is capital K, all right? So, well, that's where we have to go. We got to look at how we make combinations of these 4 fundamental properties and their units. So now let me see if I can zoom in on that a little bit. So these are the metric prefixes that they say are commonly used in physics. Actually, you'll be using a whole lot fewer of these metric prefixes. And here's the thing, I don't need you memorizing them at all, okay? This class is absolutely not about memorization. This class at its core is about, here's the information, utilize it when you need to. So if you need to have a chart with metric prefixes available to you as you're doing your work, whether it's on an exam or on a homework assignment, use it. I don't want you memorizing anything, okay? So let's talk about this table, all right? So as you probably can reason, when we make measurements, we don't always measure one. Our measurements aren't always 1 meter, 1 kilogram, 1 second, 1 Kelvin. When we measure, many times we measure more than one, and many times we measure less than one. So sometimes we measure multiples of our base, and sometimes we measure fractions of our base. So this table has a way of communicating multiples and fractions of our base units, okay? And those multiples and fractions are based on powers of 10. That's typically what you associate the metric system being. You associate it with powers of 10. And so what we've done is we've taken those powers of 10. When I say power, I mean the exponent. We've taken those powers of 10 and we've given them a prefix and an abbreviation. So for example, on this table, you can see that there is a power of 10, 10 to the 6. And that power 10 to the 6 represents 1,000,000. So we would have 1,000,000 times our base. And we use the prefix mega to be associated with that power of 10. And then we use the capital M to represent that prefix mega, okay? So by utilizing prefixes, we can communicate, because that's what this is all about, a systematic way of communicating, right? We can communicate, in this particular case, a mega, multiples of our base, all right? So again, you don't have to memorize this chart, but you do have to be able to utilize it. And Wednesday, we'll see, we'll put in play actual usage of these prefixes to begin understanding measurement, okay? So what we want to focus on Wednesday, because we have about 5 minutes left, is we're going to be looking at the idea of unit conversions. Okay, so what I'll do on Wednesday is I'll give you an introduction to the project. We'll look at the idea of derived properties and derived units, and then we'll talk about unit conversions. Okay, so that's what we have left on our plate for this week. So I like to take the last 5 minutes, I'll stop sharing and give you an opportunity to ask questions that you might have about anything that I've covered.
I have a question.
Yes, sure.
I'm just looking at all the assignments. I'm just gonna ask the question just where I can have an understanding of everything.
Yes, ma'am, sure, go right ahead.
For the graph and post lab discussion.
Okay, so you're in lab class.
Oh wait, I'm sorry. Hold on. Let me go to lecture. I'm sorry.
Yeah, because I'll answer questions about lab during lab time.
I'm sorry. Hold on 1 second. So the measurement 2 discussion session. So are we answering the basic questions at the bottom where you have please post your answers and replies to the discussion questions below?
Yeah.
So we're basically answering the questions that's underneath there, correct?
Yeah, so it gives you here in the directions here. I'm sharing the screen. Be sure to comment on at least 2 of your classmates' postings, right? You said, please post your answers and your replies to the questions below. So you answer the questions and then you have to respond to what 2 of your classmates post for their answers, okay?
Okay, and then for the nature of science discussion, is basically the same thing. You want us to answer the questions and then reply to 2 of our classmates, correct?
That's correct. That's what any discussion that you do for me follows that basic format.
Yes.
You answer the questions and then you respond to your classmates.
And then for the PS number 1,
right?
So you want us to basically do every single thing that's on there, correct?
Correct. So part A tells you to use the scientific method to investigate a simple problem of your choice. The steps are listed in the lecture notes, and I actually did an example of that when I did the did the over the top example of the Titanic. So now you get your opportunity to make up your own answers to utilizing the scientific method, right? And then in part B, this deals with units. So, we still have some stuff to cover on that, but, by the time we're finished on Wednesday, you should be able to, fill in, answer the questions relating to units. And then this last part C, just reminding you have to make sure you show your work. This deals with derived properties, and that's one of the things also on Wednesday that I'll be focusing on. So by the time I finish on Wednesday, you will have what you need to do both discussions and the problem set that is due by the 12th.
Okay, my last question. Should we, because I want to start on these all these assignments, should I wait to do something until Wednesday? Which assignment would you consider to do today or tomorrow?
I leave that up to the students' judgment. There are some students who have no issue with going into the resources that I provided, looking at the videos, looking at the notes, and then they're able to do that all on their own. And and some of them will have to do that because all of them aren't here today, right? So, some students have opted that, they don't need to attend lectures. They can do it all on their own. And so you work at your own pace. If something's not clear to you, I would advise you to definitely ask a question before you submit the work, right? To make sure that you understand correctly, right? But that doesn't prevent you from working ahead. My only rule is that you can't turn in things late. I never said you couldn't turn in anything early.
Yeah, I know. I was just asking I was just asking a general question. That's all I was doing.
Oh, no problem. Not at all. Right. So yeah, I want, my requirement is that by the 12th, you turn those items in. If you need to ask me something about them prior to, feel free.
Another question. I know last class we didn't have to go to the lab, so we still have to log into the lab after listening to this lecture, right?
Yeah, once lecture is over, then I'm gonna sign out of this, and then I'm gonna sign into the lab because it's a totally different link. And this week is not like last week, right? Because last week it was just an introduction, and it was introduction for both classes. And
okay.
But this week we're going to actually get into some things that are relevant for the lab class in terms of your first experiments. So if you're not there, you won't get you won't be able to interact with me while I'm explaining.
Did you take the roll call, or you do that?
I don't take roll. I don't
okay.
Roll. I don't give points for attendance. I tell these students that's I'm here to provide a service. I'm sharing the information with you. If you come and get it, fine. If you watch the video, fine. If you don't come and you still do the work, fine. It's up to you.
Okay.
Any other questions? Please feel free.
I have one more. I'm sorry.
Yes,
I'm just trying to. As far as the assignments, are you grading how do you grade your assignments, if you don't mind me asking, just on the material that we have to do? How are you? I know each thing is graded.
The discussion, if you look under assignments and activities, it tells you how I grade problem sets. And if you look at the discussion information, it tells you how I grade discussions.
Yes. Okay.
Any other questions? Please shoot.
I have a question on your project.
Yes, I'm gonna talk about the project on Wednesday, but please feel free to ask your question.
Okay, I was reading over it and I just want to get a clear understanding on what do you want. Because I see a summary and then I saw like a 15-page. Is
No,
this
you
all
don't.
together or I'm just reading
Yeah,
separate?
yeah, you're definitely not gonna
Okay.
be writing anything 15 pages long, because
Okay.
it tells you in there your article, not your summary, must be 15 pages long, right? So I'm gonna give you enough information on Wednesday so that you can get started on the project. But
Okay.
if you have a specific question that you want to ask me, I'll be more than happy. But for the more general coverage, I'm gonna do that on Wednesday.
Okay.
Yeah,
All right. Thank you.
sure. Any other questions?
One more question pertaining to the project. I know you're gonna go over it on Wednesday. That week of the project, are we just working on the project or will we have other assignments also due at the same time?
You're talking about what? You said you're looking at what down here at the weekly overview when the project is due?
Yeah, so we just have the project due that week. Are we having,
Well,
application?
if you look at week 7 on the weekly overview, you can see there is another
yeah,
overview there.
for some reason, mine's not downloading like that. I'm looking at your screen, mine's not doing that for some reason. That's why I'm asking.
So are you able to click on the items on the left side menu?
Yes, I'm on the regular website, but every time I go to the activity part, it's not, I don't know if it's my
Yeah, well,
tablet.
okay, my question to you is, did you log into Canvas from Nunez or did you log into
Yes.
Canvas from another school?
No, I logged in off of Nunez's website.
Okay, so if you look at the front here, it says Nunez.instructure.
Yes.
Okay, so you should be able to utilize all the items on this left side menu.
I don't know, mine's not fully popping up. It might be my, I don't know, it might.
So what are you looking for?
I was just asking about the thing for the same week. Are we doing for the project? Do we have an assignment due also? That's all I was asking.
So are you able to click on the weekly overview?
I'm able to click on it, but after that, it's just nothing's loading after that. I don't know, like I said, I think it's my tablet. I don't know if it's my tablet or.
Okay, well, I mean, at some point you're gonna really need to have access to the weekly overview, because if you do.
It was loading last week. It's just, I don't know, for some reason it's not loading today. I don't know what's going on with it.
Okay, that part, unfortunately, I can't help you with, but if you are able to, at some point, you'll see in week 7, you do have more than just a project due.
Okay, thank you.
Yes, ma'am. Any other questions? Please shoot. I do have a few minutes before lab class starts, so I'm happy to address it. If you don't have any questions and you're good in terms of what I've covered, feel free. We're done, but I'm happy to hang around for a few and answer any questions that other students might have. All right, so I'll take that as everybody's good and there are no more questions. So I'm gonna stop sharing and we're done. I will post this recording as soon as I get from YouTube the captioned version of the video. So thank you for joining in this evening, and I'll see you back here on Wednesday.